Hello, welcome to the part 2 of the e-lecture series on the subject of theory of machines. In this part, we will be covering the chapter 1 of in the subject of theory of machines, which is mechanism. The subject of theory of machines is divided into 4 main chapters as follows: mechanisms, gear trains, flywheels, and vibrations. In the chapter 1, which is mechanisms, we will be covering the following topics. We will have an introduction on the subject, basic definitions in mechanism formation, theory of mechanism formation, and some solved examples. Then we will move on to a typical example of mechanism, that is a 4-bar linkage. We will do velocity analysis in the 4-bar linkage. Then we will move to the example of slider crank mechanism, which is a derivation of from the 4-bar linkage mechanism. And then we will be doing some questions and solved examples. The topic of gear trains and flywheels also come under the subject of mechanisms if you look at the Gates level. However, these two topics are quite involved, and that's why they will be covered as a separate chapter. So gear trains will form the chapter 2 of the subject, while the flywheels will form chapter 3 of the subject. In the last part of the lecture series on theory of machines, we will cover vibrations. So in the chapter 1, we will be considering the mechanisms, particularly the slider crank mechanism, and the 4-bar linkage, which you can see here. Now, we come to the basic definition of the mechanism. A mechanism can be defined as a system of rigid elements, which are called links, which are arranged and connected by joints to transmit motion in a predetermined fashion. So, as we have already discussed, the mechanism formation is needed to transfer velocity and forces from one location to the another. So, mechanism is used to convert one form of motion to another, like from rotary to translational, etc. Or in a broad manner, it is a system to convert a form of available motion, that is the input motion, to a desired motion. So it helps us to achieve that. Now, the basic building block of a mechanism, as you can see here from this statement, are links and joints. So a mechanism is a system. System means it's an assembly of various other subsystems, components, that is having links and joints. So now we will go through basic definitions. After we have defined the mechanism, we will go through basic definitions of various stages in mechanism formation. The basic building block is link. Link is defined as a rigid body. So there is no internal movement of flexing or buckling of that component is allowed in mechanism analysis. When it is considered as a link, in a mechanism, the body should be rigid. There should not be any deformation of that body. So if that condition of rigidity is maintained, this will help us to get the predetermined motion. Only then we can achieve the predetermined motion of components if rigidity is there. So link is a rigid body or a resistant body forming part of mechanism. We will visualize the concept of links and joints with the help of a simple mechanism that is available in our day-to-day life, that is a bicycle. Now here we can easily see various links and joints. So we have a pedal which is connected by a rigid joint to the sprocket wheel, and then the sprocket wheel is driving through the sprocket chain the smaller sprocket. The smaller sprocket is driving the back wheel and it's propelling it forward, the entire cycle forward. Here in the front wheel we have the direction control. So we have handle. The handle can be rotated in the direction normal to the direction of perpendicular to the direction of motion to control the direction of cycle. So as you can see here, this handle is a link. Also, this front tire is a link, front wheel is a link, back wheel is a link, the sprockets are linked, the sprocket chain is a link, the pedal is a link. So all of these are links. So if I number these links in different numbers, L5, L6, L7, etc. So all the links are connected together through various joints. The link 3, pedal to sprocket, is connected by a rigid joint. And link 7 is connected to link 6 through a sprocket joint, which is no slip joint, friction joint. And then the same friction joint is connecting L6 to L5. And then there is a rigid connection between link 5, the sprocket, and the the back wheel, and the link 1 is connected to the body. The body also you can consider as a link, link 8. So these two are connected by a pin joint. So there are various links and various joints, J1, J2, J3, J4. So this is example just for your help you to visualize the concept of links and joint, and the same definition you can extend to any mechanism. So you can find various links and joints. So you can break down your complex machine into mechanisms, small manageable mechanisms, and these mechanisms you can further break down into links and joints, and then you can analyze as single link or joint. So that makes the analysis possible of a complex part. Now the links are pretty much simple, they are just a rigid body. So here also we have some types of links, like they are basically classified according to the number of other links they are connected to. So we have binary links which are connected to two other links. We have ternary links which connect to three other links. So here you can have one link connection, here you can have one link connection, here you can have one link connection. So this is a ternary link. The shape may vary. This is just for our definition purpose. It can be any complicated shape like this. So this is also connected to three other links. Or you can have quaternary links. The quaternary links are connected to four other links. So in the same member, if you have one more link possibility, it is a quaternary link. So all the links all the joints in the link formation need not to be same. You may have a component which is having a pin joint with some other component, and maybe it is having a sliding joint with some other link. So it will still be a binary link. So the type of joints may be different, but according to the number of joints in a link, to how many other links it will be connected, they are classified as binary, ternary, or quaternary links. So after this, we will come to the next other building block of the mechanism, that is joints. The basic definition of a joint is that it connects two links and it allows relative motion between two links. So, if a joint is connecting two bodies, but it doesn't allow relative motion between these two bodies, then it can't be classified as a joint as per the mechanism definition. In this case, the link 1 and link 2 will be a single link named as L. However, if the joint allows relative motion, then it can be considered as a joint in the mechanism definition. Now I will give you some examples of joint. The simplest example is a pin joint that you can see here on the right hand side. In this joint, there is a link having a cylindrical hole surface, and there is another link which is also having the pin through a hole inside it. So a pin connects these two links. It allows the angular motion of one link with respect to other. Another example would be a sliding joint. The sliding joint we see in the case of internal combustion engines. So there we see a piston moves inside a liner. So there is a cylindrical surface of contact. Now if you compare the piston liner joint to a pin joint, both are having a cylindrical surface in contact. However, in a pin joint, the relative motion between two links is of angular nature, while in a piston liner arrangement it is linear. So if you have linear motion, then the joint is named as sliding joint. The surface of contact may not be necessarily cylindrical. It may be planar also, or a line contact also. For example, a drawer in a wardrobe is residing on railings inside the wardrobe, and here the sliding motion takes place. Similarly, you have in your apartment, you can see the windows, sliding windows. So here the window slides in a frame. So these are sliding joints. The common thing between a pin joint and a sliding joint is that both of them are surface joints. So there is a surface to surface contact. There are other examples such as gear joint. In gear joint, we see a line-to-line contact. So this will be explained in much more detail in chapter 2, which is dedicated to gears. But when we analyze the motion of two teeth together, you will see that there is only a line contact. So in a gear, what happens is that there is a contact between two teeth of either side, and one teeth pushes the another. So both the surfaces move together. So this is a special kind of joint, the gear joint, because here at the point of contact there is no relative motion, but if you consider link 1 and link 2, there is a relative angular motion between the two joints. So this is a kind of special joint. Another example of a line joint is cam. In a cam, we have an oval member, oval link, which is having its axis eccentric to its center. Because of that, the radius of this member is different at different angular positions. So this cam is rotating in angular fashion, and it is supporting a linear member which is constrained by a sliding joint. As the cam rotates, results in the linear motion of the linear sliding member. So as we discussed, the cam and the gear joints are line joints, while a pin and sliding contact are surface joints. There can be other variety of joints which cannot be classified in either of these categories. That is a friction joint. For example, you can visualize two cylinders that are sometimes used in rolling press that are pushed together by an axial force. So there is a normal force at the contact surface of two cylinders, and then both cylinders are rotating in counter direction. So in this case, there is friction between the mating surface. In this region, if you zoom in, you will find that the structure will be somewhat like this. There will be a finite extent of contact, and due to the friction force between the two mating surfaces, the two surfaces are kept together. And a very much simpler example for this friction joint is a wheel moving on land. So in this case, if you consider R1 as the radius of this body and R2 as the radius of this body, in this case R2 becomes infinity. That is land, and this is a wheel. So both these two things are joined by a friction joint. This joint, friction joint, is not so rigid in terms of relative motion between the components. In friction joint, the slip is allowed. So it is not so rigid in terms of constraining the motion. Whereas if you see a gear joint, the two teeth are in contact with each other, there cannot be any slip allowed. The velocity of link 1 and velocity of link 2 will be same. But in this case, the velocity of one wheel can be different from velocity of the other wheel. So slip is allowed. If you see the sliding joint, it is a completely slipping kind of joint. Here complete slippage is allowed. There is no constraining between the four components. These examples that you see here are various kind of joints. Some other joints that I can list here is the screw joint. So this is the surface to surface joint. Here the nut is allowed to move in a rotatory fashion while the screw moves in a linear fashion, or it can be otherwise also. The nut can be constrained, the screw can be rotating, and the nut can be moving in a linear fashion. It can be constrained in any manner. So it's a sliding surface contact. Also, you have chain sprocket. So you have two different sprockets, wheels that are having teeth, and the teeth are connected together by a chain, etc. So these are various kind of joints. Now that we have understood the concept of links and gears, we will now come to the basic building block of mechanism, that is the combination of link and gear. So as you can see here, we have one link 1 and a link 2 which are joined together by a joint, and the joint is such that it allows some relative motion between the two links. So this full system, a system of two links joined by a joint which allows a relative motion, is called a kinematic pair. The kinematic pair is defined on the basis of degrees of freedom. The concept of degrees of freedom is very important in mechanical engineering. Depending on degree of freedom, the kinematic pairs are classified as class 1, 2, 3, 4, 5, etc. degree kinematic pair. The class 1 means that the kinematic pair is having 1 degree of freedom. So we will be using the abbreviation DOF for degree of freedom. We will deviate a bit from our regular topic of links and joints and mechanisms to delve over the subject of degree of freedom, because it is very important to understand mechanism formation and how the constraints are applied in a joint. So, if you consider a rigid body in three-dimensional space, x-axis, y-axis, z-axis. So, if you consider a rigid body of any shape, arbitrary shape, it may be a link, it may be a solid body in space, it basically has 6 degrees of freedom. One is along x-axis, translational, one is translational along y-axis, one is translational along z-axis. Likewise, there is rotational degree of freedom along x-axis, y-axis and z-axis respectively. Similarly, in a 2D system of coordinates, we are having 3 degrees of freedom. So object has x direction, y directional, translational capacity and a rotational degree of freedom in xy plane or along the z axis. So the purpose of a joint is to constrain a desired number of degree of freedoms. By doing this, we will constrain a mechanism to move in a predetermined fashion. All of the joints described till now, like cam, gear, pin joint, sliding joint, screw nut, etc., allow only 1 degree of freedom. So in a pin joint, it is a rotational degree of freedom, and of link 2 with respect to link 1. There can't be any translation of link 2 with respect to link 1. There can't be any moment in the other planes of rotation. So only one rotational plane is allowed. Similarly, in a sliding joint, only a linear degree of freedom is allowed.
There can't be any rotation. So these things, like in piston, liner piston arrangement, there is only 1 degree of freedom, that is translational. However, it can be arranged in some other manner, like you have a cylindrical surface of contact, outer surface and an inner cylinder. So the cylinder, if you see the cross section, it may have a linear degree of freedom also, it may have a rotational degree of freedom also. So it depends how we are forming the joint, what are the degree of freedoms you are willing to allow. That is why we classify a kinematic pair, which is nothing but two links joined by a joint that I just described, by degree of freedom. So a class 1 kinematic pair has 1 degree of freedom. Similarly, a class n kinetic pair has n degree of freedoms. So in a 3D system, a class n kinetic pair will allow n DOF and it will constrain 6 minus n degree of freedoms. In 2D, the allowed are n and the constrained are 3 minus n degree of freedom. Because in 2D we have basically 3 degrees of freedom, that is the maximum degrees of freedom. In 3D we have 6 maximum degrees of freedom. So out of that, all 6, if n only n number of degrees of freedom are allowed, then all the others are constrained. This is a simple definition for a class n kinematic pair. We will just note here that lower classes of kinematic pair are more constraining, and we have the pair moving in more predetermined fashion. If you go for higher kinematic pairs, that you can see example of a cylinder resting on a surface or a ball resting on surface. So it is having translational along this direction, the other direction. It is also having a rotational degree of freedom. A spherical ball landing on staying on the ground is having 5 degree of freedoms. So it can rotate above any axis 3 degree of freedoms, and it can translate along x and y axis. So, but these kind of kinematic pairs which are having more degree of freedoms are rarely useful in machine design. So, in machine design, we will normally encounter a class 1 or at the max class 2 kinematic pair. The kinematic pairs are also classified on the basis of nature of relative motion between the contact surfaces at a joint. So like this, they can be classified as a rotary pair or revolute pair. So the example would be a pin joint. We have sliding or prismatic pairs. The example would be the sliding joint. The movement can be either surface to surface contact, or there can be a line contact, but there is a sliding motion. That is the primary definition of this category. Another category is the cylindrical pair. Under this category, we get gears, cams. Point of view of the degree of freedoms allowed in a pair. In a rotary or revolute pair, you can see that only 1 degree of freedom of link is allowed with related to the other. So we have here 1 degree of freedom in a kinematic pair, and 5 degrees of freedom are constrained. So this is a class 1 kinematic pair. Similarly, for a sliding joint, there is only linear motion allowed with respect to the other link. So here also the degree of freedom is 1. In a cylindrical pair such as gears and cams, we allow normally a predetermined relative motion between the two components, and also the axial movement. Like if you see along the paper in the direction normal to the paper, these two wheels can shift in axial direction relative to each other. Similarly, here in cam, there is a predetermined relative angular motion and a linear motion, and also it can go in axial direction. That is also allowed. So here we have 2 degrees of freedom. The other kinematic pairs are a planar pair, which you can visualize like a plane surface in contact, like a box kept on plane surface. So here you have 2 degrees of translational motion and 1 degree of rotational error. So here we have 3 degrees of freedom for a planar pair. Also we have a spherical pair. So spherical pair is a special example. We don't know whether you are aware of it. Like there is a joint called knuckle joint. So here there is a spherical surface, like almost spherical surface. Inside that a ball goes and sits here. So in such a fashion that all kind of angular motions of this ball relative to this spherical cover are allowed. So all 3 angular. So it is a class 3 kinematic pair. Based on the nature of contact, there is a classification of kinematic pairs. So here we have higher pairs and lower pairs. So higher pairs are the one when we have a line or point contact. And the lower pair is the one where we have a surface contact. So the pin joint, the sliding joint, all of these are lower pairs. And the gear, cam are having line contact and they are higher pairs. The point contact you may visualize like in a case of a spinning top on with the ground, there is a point contact. So it can have all kind of angular motions along all 3 axes, but it can't have any translational motion. So this is a point contact joint, and it is called a higher pair. Another classification of kinematic pair is based on the type of closure. If the joints are so formed that they are held together by shape and cannot be detached easily, they are called form closure. The pin joint or a window sliding in the frame is an example of this joint, kinematic pair. The other category is force closure. In this category, the links are held together by an external force. The spring loading For example, they can be separated easily.